This lesson is about independent and mutually exclusive events. Here are some notes that you should write down right from the start and refer back to later. Mutually exclusive events. These are events that cannot occur at the same time. You can tell from the Venn diagram. So there will be no intersection between them. These are or events. We talk about whether A happens or B happens. And there's an addition rule that we're going to use. Should I go ahead and write that down now? The probability of event A or B, and that's how you read it with when you have a U like this for union, you say or, is going to equal the probability excuse me, of event A plus the probability of event B. All right, that's the addition rule. On the other hand, talking about whether two events are independent, that's a completely different concept. Independent events can occur at the same time. You can tell by the way these circles are overlapping in the Venn diagram. So you can have an intersection, and we usually wind up talking about and events because we want to know what is the likelihood that event A and B will happen at the same time. We want to know about the overlap. And to figure that out, we use the multiplication rule. When you have independent events, it turns out that the probability that event A and event B will happen, and when you use the intersection symbol, this upside down U, you say and. That turns out to be the product of the individual probabilities. So that's the probability of A times the probability of B. All right, we'll talk more about this, but you should write all this down. In a standard deck of cards, there are 4 suits: spades, clubs, hearts, and diamonds. Each suit has one each of 13 cards: ace, king, queen, jack, and then the numbers 2 through 10. If event A is choosing a king, event B is choosing a heart, and event C is choosing a jack, which Venn diagram could represent this description? First, here's a quick glance at what they're talking about. This is a standard deck of cards. Here are what they mean when they talk about the 4 suits. There are clubs, spades, hearts, and diamonds. All right, the 4 suits. And within each suit, you have an ace, a jack, a queen, and a king. And then also the numbers 2 through 10. All right, for each suit. So that's a quick glance of what they're talking about in case you are not familiar with what cards are. So event A is choosing a king, event B is choosing a heart, event C is choosing a jack. Let's talk about which of these events are mutually exclusive. In other words, some of these events cannot happen at the same time. So, for example, can you be a king and a heart at the same time? Well, sure you can. You could be the king of hearts. You can be a king and a heart at the same time. So, event A and event B are not mutually exclusive. They can both happen at the same time. Can you be a heart and a jack at the same time? Sure, you can be the jack of hearts. All right, so event B and event C are not mutually exclusive. Now, these are the ones that are mutually exclusive. You cannot be a king and a jack at the same time. You're either a king or jack. You can't be a king jack. So when we look at the Venn diagrams, we're looking for diagrams where there is no intersection between A and C, because those are mutually exclusive. I'm going to say ME for mutually exclusive. All right, so we're looking for A. Let me draw this bigger. We're looking for event A and event C to definitely have no overlap between them, because they're mutually exclusive. On the other hand, event B of being a heart, that could overlap either one of these. All right, so there should be overlap between with event B. So we're looking for something like this, where A and C don't touch, but A and B have overlap, all right, and B and C have overlap. That's what we're looking for. So let's see, which one is that? We can throw out this one because none of those are touching. Okay. Let's see. Look at this one here on the upper left. A and C are not touching, but B is touching them both. I think that's the one we want right there. Here we have all three touching. That's no good. Here we have A and C touching. Nope, A and C we're supposed to be mutually exclusive. So it has to be this first one. Okay, which scenario depicts two independent events? If you have two events that are independent, then one event does not have any effect on the other. All right, look at the first option. The school play opens tonight and it is raining. Well, I'm pretty sure that these are two independent events, because the school play is going to open regardless of whether or not it's raining. And whether it rains or not is not going to be affected by whether or not the school play happens. So these are completely independent, so that would be my vote. Now let's look at the rest and see why they are not independent. Neva is hungry and she buys a snack from the concession stand. Well, if Neva is hungry, she's more likely to buy a snack from the concession stand. And if Neva buys a snack from the concession stand, she's less likely to be hungry. So those are dependent. Ari chooses a partner for a group project, and then Ezekiel chooses a partner from the remaining classmates. Well, the fact that Ari chose a partner first, that took up one of the potential partners. So that affects Ezekiel's choices, because he has one fewer choice now than he had before. So his probability of choosing a partner is decreased by one person. So those are dependent. Luca paints during school and he stains his shirt. Those are not independent, because if Luca paints, he's more likely to stain his shirt. A month of the year is chosen at random. What is the probability that the month starts with the letter J or the letter M? Well, the probability of an event happening is always going to be the target number of events divided by the total number of events. Target over total. Now, a month of the year is chosen at random. We know that there are 12 months in a year. So, if we want the probability of choosing one that starts with J or M, then we're going to need to add and see how many months have J and how many months have M, and we'll wind up adding those together. All right, I think I got this. January, February, March, April, May, June, July, August, September, October, November, December. So I've color coordinated this to make it easier to see. There are 3 months that start with the letter J, and there are 2 months that start with the letter M. All right. Whoops, I put M and I forgot to put 2. That means the probability of picking a month that starts with the letter J or M is going to be 5/12. Okay, and there you go. Now notice, using the language of mutually exclusive events. All right, understand that these two events, all right, we're talking about the probability of picking a month that starts with the letter J, and we're talking about the probability of picking a month that starts with the letter M. If you pick a single month, it can't start with J and M. It's going to be one or the other, or neither, but it definitely cannot be both. So these are mutually exclusive. And when you have events that are mutually exclusive, then if you want the probability of one thing happening or the other, and this is the symbol that we use when we say or, the union symbol, then we can add. So we could say the probability of J plus the probability of M. All right, the probability of picking a month that starts with J was 3/12. The probability of picking a month that starts with the letter M was 2/12. Add them up, and that's 5/12. So that's another way to talk about it. A bicycle manufacturer is studying the reliability of one of its models. The study finds that the probability of a brake defect is 4%, and the probability of both a brake defect and a chain defect is 1%. If the probability of a defect with the brakes or the chain is 6%, what is the probability of a chain defect? Okay, well here's what they're getting at. Here is the formula for when you're talking about events that are not mutually exclusive. Apparently, the event of having a brake defect and the event of having a chain defect, these are not mutually exclusive because they're talking about the probability of both things happening. The probability of having both a brake defect and a chain defect is 1%. Okay, if they can both happen at the same time, and then there's some overlap here. So here's the formula for finding the probability of event. Let's see, we're talking about brake and chain. So if I want the probability of a brake failure or the probability of a chain failure. Okay, now if these events were mutually exclusive, brake failure, chain failure, all right, no overlap between them, then if I want the probability of one or the other, then I would just add the probability of brake failure plus the probability of chain failure. But when there's an overlap between these, okay, so let me redo it. You've got your brake failure and kabam, you've got your chain failure, but oh look, we got some overlap in here. All right, when there's overlap between the two, you have to subtract the overlap because you're counting it twice. All right, when I did the probability of B and then I did the probability of C, both of those include the overlap. So I'm counting the overlapping area twice. So I need to subtract the overlapping area once to get rid of the extra. So the overlapping area is called the intersection of B and C, and we write it this way: B intersection C. Okay, so we need to subtract that. So we need to subtract the probability of the intersection of B and C when they overlap. Okay, so it's a slight modification to the addition rule for mutually exclusive events. All right, so anyway, within this story, they've given us 3 out of 4 of these pieces of information, and we need to solve for the 4th one. All right, so let's see what they've given us. All right, so the study finds that the probability of a break defect is 4%. Okay, so break defect, 4%. All right, that's the probability of B. All right, that's your break defect. So they're telling us that this is 4%. And 4% is the same thing as 0.04. So I'm just going to go ahead and put that. What else are they giving us? The probability of both a break defect and a chain defect is 1%. Okay, and that's your intersection right here. So this is where they're giving us the probability of break defect and chain defect. They're giving us this intersection. All right, so they're telling us that this is 1%. That's 0.01. All right, what else are they giving us? If the probability of a defect with brakes or the chain is 6%. Okay, now as soon as they say or, they're talking about this symbol right here. In fact, look, get this down right now. When we talk about and, we're talking about the intersection symbol. All right, and this are the same thing. When we talk about or, we're talking about this. So you need to memorize that fact. All right, so when they say the probability of a defect with brakes or chain, this is the probability of brakes or chain right here. And they're telling us that that is 6%. Okay, so this thing right here is 6% or 0.06. Okay, so they gave us 3 pieces of information out of the 4. The only piece of information that they did not give us from this formula was this, the probability of a chain defect. And guess what? That's what they're asking us for, the probability of a chain defect. All right, so just rewriting this equation using all the numbers that we just saw, what we have is 0.06 is equal to, I like to put a 0 in front, 0.04 plus the probability of a chain defect minus 0.01. All right, we just substituted everything they gave us into the equation. All right, so please make sure you add this equation to your notes. So now I just need to solve this for the probability of a chain defect. I'm going to go ahead and put these two together because they're like terms. 0.04 minus 0.01. You probably don't need a calculator for that. You can probably guess that that'll be 0.03. Okay, so then what I have is 0.06 is equal to the probability of a chain defect plus 0.03. I just combined my like terms there. Now to get the probability of a chain defect by itself, I will simply subtract the 0.03 from both sides. I hate it when it does that. Okay, again, you probably don't need a calculator for this. You can probably guess that this will be 0.03. Okay, which is the same thing as 3%. All right, there you go. Looking back, I'm realizing it was completely unnecessary for me to convert these whole numbers into decimals the way I did. I probably should have just left it as 6%, 4%, and 1%. So the equation would have been 6% is equal to 4% plus probability of chain defect minus 1%. Combine your like terms, 3%, subtract 3% from both sides, you get 3%. There's no need for the decimals. So a bag contains 11 equally sized marbles, which are numbered. What is the probability that a marble chosen at random is shaded or is labeled with a multiple of 3? So look, there are two formulas basically that we are learning in this section. One has to do with the union of two events, so like this. And one has to do with the intersection of two events, so like this. Okay, so my first question to you is, which situation are we in? All right, are we in the union situation or the intersection situation? All right, the top one or the bottom one? All right, because that's going to dictate which formula we're going to break out with. And here's the key. What is the probability that a marble chosen at random is shaded or is labeled with a multiple of 3? Okay, so shaded, multiple of 3. Those are the events, but in between them we have this word or. So the real question is, which one of these symbols represents the word or? Is it the top one or the bottom one? Hopefully you remembered from earlier in the video, the union symbol here is the same as or. The intersection symbol is the same as and. Okay, so we should be dealing with the top equation. All right, when you're talking about something or something, we're going to be dealing with this. Now, here's the equation. If you want to find the probability of A or B, then this is the one where we do an addition rule. Okay, so we do the probability of A plus the probability of B. All right, but here's the thing. If there's any overlap between the two events, you have to subtract the overlapping part. In other words, are these mutually exclusive, or can they happen at the same time? Can you be shaded and be a multiple of 3? Yes. All right, look at some of these. All right, you can be shaded and be a multiple of 3. So there's overlap between these two things. So whenever that happens, you need to subtract the overlapping part. All right, you need to subtract the intersection. All right, I'm trying to squeeze this in here. All right, so that's the complete formula. So the probability of A or B is the probability of A plus the whoa, that was supposed to be a P, plus the probability of B minus the overlapping part, minus the intersection. Okay? Okay, so let's let event A be the whole shaded thing. Okay, let me use this space up here. All right, event A will be shaded, and event B will be multiple of 3. Okay, so let's calculate the probability of A and the probability of B. All right, so the probability of picking a shaded one. Well, let's see, we have a total of 11. Okay, so I'm going to put 11 in the denominator. Let's see, 1, 2, 3, 4, 5 are shaded. So the probability of picking a shaded one is 5 over 11. Now, let's talk about the probability of picking a multiple of 3. All right, the probability of event B. Well, again, the total number of marbles is 11. So the probability of picking a multiple of 3, let's see how many of those there are. Okay, so 3, 6, 9, that's it. All right, 3, 6, and 9. So those are the ones that are multiples of 3. So there are 3 of them. So 3 out of 11, that's the probability of event B, picking a multiple of 3. Now let's figure out what's the probability of A and B. What's the probability of being in the overlapping part? Okay, so let's see. The probability of A and B. Okay, let's see. Which are those? So we're looking for ones that are shaded and multiples of 3. Got 'em. Got 'em. All right, so there's 2 of those. There are 2 in the intersection. So the probability of being in the overlapping part is 2 out of 11. Okay, so the probability of A or B then should be the sum of the first 2 minus the third one. Okay, so 5/11 plus 3/11 minus 2/11. Well, 5/11 plus 3/11 is 8/11. And then, all right, so we've got 8/11. And then 8/11 minus 2/11 is 6/11. So that should be the overall probability of event A or B, 6/11. All right, and there you go. Now, here's another way to think about it if you wanted to just use your common sense instead of trying to use a formula. All right, I'm going to do the whole problem again real quick using common sense. All right, in general, probability is always going to be the target number of outcomes divided by the total number of outcomes. Target over total. Okay. There are 11 marbles. So that was definitely the total number of outcomes. Was definitely going to be 11. Now, in terms of the target number of outcomes, we wanted to find the probability of choosing a shaded one or one that's a multiple of 3. So shaded or multiple of 3. Okay, so we know the denominator is going to be 11. All we need to do is figure out how many marbles are either shaded or a multiple of 3. So you could just count. All right, let's start with shaded ones. Boom, 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 boom. So we've got those shaded. Let's see. So now we can just look for how many ones that we haven't already shaded, because obviously we don't want to count anything twice. So how many of the ones that we haven't shaded yet are multiples of 3? So we've done shaded. How about multiples of 3? All right, 6 is a multiple of 3. 10, 11, 2, 7, 8. Nope, that's it. So we just count up how many are in the target group. How many are there that are shaded or a multiple of 3? Turns out 1, 2, 3, 4, 5, 6. There are 6 marbles that are either shaded or a multiple of 3. So 6 out of 11, common sense. The Hawaiian language has 12 letters, 5 vowels, and 7 consonants. What? Is that true? I'm going to have to Google that later. Each of the 12 Hawaiian letters are written on a slip of paper and placed in the bag. A letter is randomly chosen from the bag and then replaced. Then a second letter is randomly chosen from the bag. What is the probability that two vowels are chosen? Okay. All right, because we are putting the first letter back. So we're choosing a letter out of the bag and we're replacing it. And then we're taking out the second letter. Because we're putting the first letter back, then these two events are independent. All right, one event does not affect the other because each when you pick the second letter, you have a fresh bag with all 12 letters again. That's important because that means if we want to find the probability of two events happening and they are independent, then we can use the multiplication rule for independent events. So we're saying the probability of event A and event B happening when they are independent events is going to be the probability of event A times the probability of event B. Okay, so here's the deal. A letter is randomly chosen from the bag, then a second letter is randomly chosen. What's the probability that two vowels are chosen? So, the probability of choosing a vowel, let's figure out what the probability of choosing a vowel is first of all. So, there are 12 letters total. And how many vowels are there? There are 5 vowels. So the probability of choosing a vowel is 5 out of 12. All right, keep that in mind. So that means the probability of choosing a vowel twice. That means probability of choosing a vowel and another vowel. Okay, that's going to be the probability of choosing a vowel times the probability of choosing a vowel, all right, using the multiplication rule. So that should be 5/12 times 5/12. So that should be 25 144ths. And there you go. A bag contains 11 equally sized marbles, which are numbered. 2 marbles are chosen at random and replaced after each selection. As soon as I see that they are replaced after each selection, that immediately makes me think about the fact that these are independent events. So the probability of one event and another event happening is going to be, oh man, it bugs me when it does that, is going to be the probability of one event times the probability of the other event. So that jumps into my brain. What is the probability that the first marble chosen is shaded and the second marble chosen is odd? Okay, so they even were kind enough to use the word "and" for us as a hint that we're supposed to use this formula. Alright, so the probability of, so let's see, the first marble is shaded and the second marble is odd. So I'm going to use S for shaded and O for odd. So the probability of picking picking a shaded marble and an odd numbered marble should equal the probability of picking a shaded marble times the probability of picking an odd numbered marble. Okay, so let's figure out those individual probabilities so we can do this. So let's see, what's the probability of picking a shaded marble? So target over total, guys. The total number of marbles is 11. How many of them are shaded? 1, 2, 3, 4. Okay, so the probability of the shaded is 4 over 11. Now, what's the probability of picking an odd one? Alright, target over total. The total is still 11. Now, how many odds are there? Odds are 1, 3, 5, 7, 9, and 11. Okay, 3, 4, 5, 6. There's 6 of them. Alright, so 6 out of 11. So that means the product of both of these things happening is 4 elevenths times 6 elevenths. Okay, so that should be 24 out of 121. Kabam. Okay, this will be the last question. All freshmen, sophomores, juniors, and seniors attending a high school assembly okay, the total student attendance is shown in the table. Twice during the assembly, a student is chosen at random to assist with the presentation. After the first student has finished assisting, the student returns to the group and can be chosen a second time. What is the probability that the first student chosen is a senior and the second student chosen is a sophomore? So, notice that after the first student is chosen, they are sent back into the group, and they could even be picked again. So that makes these two events of choosing students independent. So right away that tells me that I could use this rule once again. The probability of event A and B both happening should be the product of the two events. Okay, that's what happens when you start fresh each time, and that's what they described. So, let's see. Okay, so that means, so reading again, what's the probability that the first student is a senior and the second student is a sophomore? Alright, since senior and sophomore both start with S, let's go ahead and stick with A and B. We'll let A represent the probability of picking a senior, and we'll let B represent the probability of picking a sophomore. Alright, so let's calculate the probability of choosing a senior. Target over total. The number of seniors is 22. The total number of students is whatever we get if we add all these up. I got 80. Alright, that will reduce. Should I reduce this? Yeah. 22 over 80. That's 11/40. Alright, now let's calculate the probability of picking a sophomore. Well, there's 10 of those out of 80, which of course is 1/8. Alright, so the probability of both things happening in a row, I messed up by putting A there first, but probability of A and B happening in a row should be 11/40 times 1/8. Alright, clearly 11 times 1 is 11, and this should be 320. Alright, let's see what the answers look like. Oh, there we go. 11 out of 320. Just like that. I hope this video was helpful to you. Good luck on your quiz.